Okay, so now let's come to this example of the work that was done at IITM, where SCC was designed by a combination of particle packing and rheology. So ultimately those two things we need to address, right? We talked about the fact that in any high performance concrete, if you maximize the aggregate fraction, you minimize the void content, right? What you have to do then is, based on the void content, decide on the amount of paste that you need to put in to get you the required workability, and the paste itself needs to be designed with an optimal rheological characteristic to have the maximum flow possible. So that was the strategy adopted here by Dr. Prakash, who did his PhD here in 2009, because currently he is at IIT Bombay. The steps in the design which were followed, one was optimization of the composition of the powder. So here fly ash was getting utilized in the SCC, but we needed to find a way to rationalize the utilization of fly ash. You can always do all kinds of trial and error. You say that I will replace 10%, 20%, 30%, 40%. Where do you stop is the question, right? So can we find a way of rationalizing the amount of mineral admixture? That was the first strategy adopted. Second was, you have a combination of aggregates, coarse, medium and fine. Can we look at a way to optimize the aggregate fraction so that we have best filling possible? Then once you have that optimization of the aggregate, how much paste is required to produce the required workability? In this case is SCC required, slump flow is what the paste is. And then finally, how do you choose a paste that is capable of providing the best properties? Okay, all of these things were looked at as steps in the design process. So in the optimization of powder composition, a simple test called the Puntka test, it's a German test, was applied. So here the name sounds complicated because it's German, but the test is very simple. It's almost like a Jugad test, you can say. So you have a container into which you fill up your combination of cement and mineral admixture, right? You fill up the combination of cement and mineral admixture, right? And you know that it's not going to have a perfect solid characteristics, that there will be some space between the particles. What you are doing is filling up water into this mixture. The water, using a dropper, you are filling up water into this beaker which has a mixture of cement and fly ash, okay. Then the water is filling up all the space between the particles, and then whatever extra water you fill up will be excess, it will come onto the surface and provide a surface sheen, right. So it's almost like your saturated but surface dry condition. That's what you want to determine. You want to saturate all the pores between the cement and fly ash particles, but you don't want to have any excess water on the surface. So what does that do? That determines the porosity in the combinations of cement and fly ash, okay. So here, instead of going to a concrete and saying I'll substitute 10, 20, 30, 40%, I'm quickly doing this test in a matter of few minutes with cement paste, okay. I'm just adding water into the mixture of cement and fly ash and seeing at what point the water is completely filling the pores and showing up on the surface like a fine sheen on the surface, okay. It's very easy to perform and you don't really need any sophistication in the apparatus. So as I said, this is the, yeah. No, that's what. This test has to be done extremely early. I'll talk about the fact that you can use other liquids also in the same test. You're right, water may have early reactions with cement which may affect the quality of the test. So you can test it with other liquids also that are equally capable of doing this. So this is a mixture of humid cement particles, cement and fly ash combination, and this is a mixture at the point of time where all pores have been filled and just the surface, one small sheen is showing up on the surface, okay. There is a glossy appearance. At that point of time you say that that's the water content which is equivalent to the amount of water that is required to fill up all the voids in this combination. Now the best combination, again we are assuming, is one which gives you least voids fraction. So you mix cement and fly ash in different combinations. So here cement percentage by volume is plotted against the packing density. Packing density is nothing but 1 minus voids content. 1 minus void content is packing density. You can also plot the same thing in terms of void content, in which case you will get graph like this, right. So here these tests were conducted, I am sorry, these circles are misplaced. This should have been on top here and here and here. Okay. So, as the cement percentage increases, the fly ash percentage decreases. So, combination has to be 100%, right. So, here this first one is only water. Water with superplasticizer, you get slightly better packing density, water with superplasticizer. And instead of water, if you use kerosene, you get a slightly higher packing density. But what you have to notice, all of it is happening at the same volume fraction of cement. All these three different liquids are giving you the same volume fraction of cement at which you are obtaining the maximum packing density. Okay, so that means this test is robust. It is able to give you a very quick answer. Matter of minutes you get an answer. Okay, so based on this, the cement to fly ash ratio was fixed at 60:40 for designing the self-compacting concrete. Okay, the next step was to look at the aggregate skeleton. So instead of using this EMMA or the particle packing software, we decided that we will go with optimization of paste, or rather optimization of powder, optimization of aggregate, then rheology of paste and rheology of concrete. So that is what I will show you. The next one was, for aggregate, how can we develop a ternary packing diagram? So first of all, empirically you can determine the extent of voids in aggregate, right. You mix the aggregate in different fractions, you fill it up in a container and determine the total mass that you fill up in the container. Then you fill up the theoretically what should be the mass based on the proportions that you have adopted, because you know the theoretical specific gravity of each of these phases. But the fact that there should be some compaction effort in this entire system is brought about by the use of this apparatus, which is a simple modification of an ASTM test, a simple test. All you do is you take up different fractions of your three types of aggregate, that is sand, 10 mm and 20 mm aggregate, mix it in different proportions, let us say 50, 20, 30, 45, 35, 20, something like that, okay, different proportions. This is all mixed aggregate, right. You pour the mixed aggregate into this top bucket. You pour the mixed aggregate into the top bucket. It has a trap door at the bottom. You open the trap door, the aggregate basically falls into the cylinder. So that is representing some level of compaction effort. You have done the compacting factor test, right. Same concept here. In the compacting factor test, you have two drops. Here you have only a single drop, right. So that just simulates some sort of a compaction. And then you measure the void content in the aggregate fraction that you get inside this container. So for different proportions of your 20 mm, 10 mm and sand, you will get different voids fractions. You choose the one which gives you lowest voids fraction, right. The problem is, how many tests can you do like this? So can you automate this process? So in this case, what we did, of course, as I said, you need to determine the void content using this density, packing density, once again is 1 minus void content. Okay. So you need to minimize the void content. So choose the aggregate combination that gives you minimum void content, but you only have a limited range of experimental choices that you can do. So in this case, what was done to ensure that we had a complete understanding of this process is to look at a sort of getting minimum experimental data and then optimizing based on a mathematical package to try and get what should be the packing density for different combinations. So here there were, essentially a ternary packing diagram was created by choosing different points which represent different combinations, right. And based on the mathematical package, the packing densities that were obtained for all these points was converted into the packing density contours. So these are contours for packing density. That means along this line, the packing density is 0.64 along this red line. Along this blue line, or whatever, I can't see the color, 0.66 is the packing density. Along this dark black line, 0.68, and there is one particular point where the packing density is 0.69. Okay. So the packing density contours can be generated by doing this kind of work. And in the chapter on high strength concrete, I described this commercial package called Europack, right? That does the same thing with just a calculation. There is no experiments there, only calculations, only a software that will help you determine the best packing density. Okay. So, using this, we arrive at combinations that can give you highest packing density. But now you see that the combinations could be anywhere, right? 0.68 packing density, 0.69 was only one point, which was, so we can discard that. Let us say 0.68 is the maximum packing density we can get, but there are so many different combinations, right? At this point, if you have to get the combination, how do you get that? You have to go basically towards each of the sides. Okay, so 60, 30 or 60, 55, 10 like that, or sorry 55, 30, 10 or 55, 30, 15 like that. So there are several combinations. But what we also understand about the basic nature of self-compacting concrete is that we want to have a combination that has a higher fine aggregate content than normal concrete. So we can then restrict the choices of our combinations to those which have a fine aggregate content of around 40 to 60%. From all these choices, from all these points, we only choose those points which will have fine aggregate content of at least close to 50% for SCC. So that is what was done in this case. I will come to that later, but ternary packing diagram is good for RMC plants where they are getting aggregates from the same source again and again and again, right. So they can actually have that database generated and then keep that for a long time for different concrete mixes. Now for an individual user, let us say tomorrow you need to go to the lab and start working. What do? You can't obviously generate the ternary packing diagram. Getting 24 data points to generate the contour plots will be very tough. Okay. So if you want to go directly in, is there a solution for this? So we wanted to again look at what aggregate characteristics are suitable for better packing. So in this case, based on the factors that affect packing density, including particle size distribution, shape of the aggregate, compaction method, and taking into consideration wall effects, it was seen that one of the parameters that has a primary influence on packing is the particle size distribution. So how is particle size distribution curve represented? You have a cumulative percentage finer versus the particle size, and if you remember your PSD calculations, you describe various coefficients, coefficient of uniformity, coefficient of curvature, and so on and so forth. So here we chose to use one of these PSD parameters, coefficient of uniformity. Okay. So again what you do here, coefficient of uniformity is basically your D60 by D10. It gives you a spread in the particle sizes basically. Okay. The particles finer than 60%, so 60% of particle finer than the size and 10% finer than the size. Okay. So now what we are trying to say is, let us adopt a simple parameter that is expressed by your particle size distribution. So now you have done individual sieve analysis for your sand 10 mm, 20 mm, put it in an Excel, do calculations of different combinations of these materials and then calculate the coefficient of uniformity. The assumption here is the higher the coefficient of uniformity, the more the range of particles between in the system. The more the range of particles, let us go back to our particle packing understanding, there will be a greater extent of packing. Okay. So that is what the idea we were trying to look at, calculating packing density based on coefficient of uniformity, and we got a fairly good correlation to describe for the aggregate that we have what could be the best possible. So of course this was determined experimentally, packing density. Coefficient of uniformity can be determined by looking at just a calculation based on different proportions of sand 20 mm and 10 mm. So this is a simpler way for a person who is starting immediately to start designing SCC. But if you have a RMC plant where you are getting a uniform source of aggregate, you can then generate those ternary packing diagrams with multiple sets of data. Okay. What is next? Once we know the packing density, let us say here 0.68, was achieved with 40% of fine aggregate, 10% of 12.5 mm aggregate and 50% of 20 mm aggregate. That was the combination that led to a good packing density of 0.68. First job was to ascertain whether our assumption is correct, whether at higher packing density you optimize the properties or not. So, look at this case here, there were 3 different combinations chosen, the packing density increases from 0.64 to 0.68. Okay. The slump flow increases from 420 to 500, the paste volume was kept constant, 388 liters per cubic meter of paste was used and the remaining 612 liters per cubic meter, because there is 1000 liters in 1 cubic meter, remaining 612 was the aggregate combination. Okay. So, here slump flow is increased, slump flow with gearing also is increased as the packing density increases, the compressive strength also increases. Now, compressive strength you are all aware of, definitely it should go up with more packing density because you have less voids. But what about slump flow and slump flow with gearing, why are they increasing? See, I have 388 liters of paste, right. Here, how much voids do I have? If I take 1 cubic meter, I have 360 liters void, no, 0.36 void content, 360 liters of void is there. Here, 340, here, 320. So, what is happening? In the first case, I have only 28 liters extra paste available. In the second case, I have 48 liters extra paste available. In the third case, I have 68 liters extra paste available. More paste, more flowability. So, this also means that now a good step to the design process is to estimate this excess paste that I require to cause the concrete to become self-compactable. These two are not proper, these two are not enough for me. I need to get to a level which is at least 600 to achieve self-compactability, right. So, here I am determining the excess paste that is required to get self-compactability. So, that is also another approach that we can take. So, one thing we confirmed here is that increase in packing density leads to an increase in flowability, leads to an increase in strength. Now, this exercise is what happens when you have the same packing density, but you have different combinations. Okay. So, you have different combinations of fine aggregate to coarse aggregate 12.5 to coarse aggregate 20. But as I said, self-compactability wise, you need to have fine aggregate content at least of 40%. So, we chose only those combinations where fine aggregate was 40 or above. So, first let us look at the strength. Same packing density, assumption is should have the same strength. Are we getting that? Yes, more or less all the things are within about 1 MPa of each other. So, definitely for the same packing density, irrespective of my aggregate combination, I am getting the same strength. But what is happening to the slump flow? What is happening to the slump flow? It is undergoing a drop when I go for very high levels of fine aggregate in my combination. So, I need to optimize the aggregate combination to a level where fine aggregates are enough to lead to a good slump flow characteristic. Okay. So, here for instance, we decided that for further tests we will go with this 50, 20, 30 ratio, 50% fine aggregate, 20% 12.5 and 30% 20 mm coarse. Okay. So, again upshot is at the same packing density irrespective of aggregate combination, you will get similar strength, but your workability will depend on the combination. So, you have to be careful about. So, again if you remember, I talked about the same thing when we discussed particle packing also. By choosing different Q values, you are increasing packing density, but you still have to look at how to provide the workability, and that is where your choice of super plasticizer, rheology of the concrete become very important. Now, again here adopting that mixed design, we wanted to look at adopting the aggregate proportions of 50 to 20 to 30. Here this is just a simple exercise doing the effect of water powder ratio and paste volume. So here slump flow is plotted against water to powder ratio, powder implying cement plus fly ash, water to powder is water to binder, same thing. Okay. Please note that this is plotted in terms of volume. In terms of mass, it will be around 0.35, 0.36 like that. Okay. What do you expect here? Obviously, as the water to powder ratio increases, your slump flow increases. What is also shown here is the slump flow increase for different powder contents, different binder content. Now, interestingly, we were also able to obtain self-compactable concrete with just 350 binder content, and that is because of the adoption of this strategy of maximizing the particle packing of the aggregate. So, even with 350 binder content we could get it, but the water to powder ratio to be adopted was 1.7, a lot of water in there. Okay. Danger of segregation is high, danger of segregation is quite high. Now, this is what I was talking about, excess paste. Okay. So, if you look at this slump flow versus paste volume, as the paste volume increases, you are expecting a higher slump flow to happen. Okay. Now, where is this 550 achieved? At around 380 paste volume. So, for an aggregate combination that gives you the best packing at a 320 liters void volume, you need at least 60 liters of excess paste to achieve self-compactability. Okay. So, that is a good starting point. Calculate void content, add 60 liters to it, that could be the paste volume that you want. That is a good starting point for a mixed design process. Instead of shooting in the dark, mixing all kinds of concretes, you can reduce the effort that you take towards approaching the design process. Again, this is the same thing, excess paste volume is plotted by subtracting the paste volume mentioned here from the, subtracting the void content from the paste volume. The same graph is repeated here and you get the excess paste volume here. And paste characteristics, rheology, you need to address separately by the test that we discussed earlier, the slump flow, the marsh cone, mini slump, and even a rheometer. Okay. So, here if you look at the water powder ratio by volume 0.8 to 1.2, the mini slump spread in this test, you see it is all in the range of 160 to 180 millimeters. So, that is a desirable range for paste that is suitable to make self-compacting concrete. And optimal dosage here is determined by a combination of your marsh cone and mini slump test. Okay. You can also do rheological studies. Of course, we have not covered the methodology of rheological studies earlier, but we looked at some geometries of rheology. This is the concentric cylinder geometry. You have the outer cylinder and the inner cylinder. The paste is filled into the outer cylinder and the inner cylinder basically is made to rotate. Okay, and then you measure the torque versus the rotation speed. So, based on that you plot the shear stress versus shear rate, and if you remember your Bingham parameter, basically it is a linear relationship where it crosses the y axis is your yield stress and the slope of this is your plastic viscosity. Now, these are all self-compactable concretes. So, yield stress as you can see is close to 0, within about 2 pascals, very small, negligible yield stress. But plastic viscosity, as the water powder ratio is increasing, the plastic viscosity decreases. More water, less viscosity in your system. Okay. So, the strategy of design of SCC encompasses several characteristics: understanding the powder combination, understanding the aggregate combination that gives the least voids content, using that void content to determine how much excess paste volume is required to get self-compactability, and designing the paste with appropriate rheological characteristics. So, that is the overall design. So, here this is just presenting you the concrete properties that were achieved with all of these water powder ratios and different binder contents. So, paste content here and aggregate content were maintained constant for all of those water powder ratios, and you can see again that as the water powder ratio increased, the slump flow increased. the T500, which is a measure of viscosity of the system, it decreased, right. As you can expect, more water, more slump flow, less viscous mix at the same paste and aggregate content, right. So, with that we stop and we come to the end of this chapter.